Welcome. I am excited to introduce Kat and Megan, longtime friends, OBTS supporters. Really excited for their talk about emulating attacker scenarios. And so, round of applause, and I'm going to hand it off to them to share the good stuff.
Happy Friday, last day of the conference. Megan and I actually have been trying to give this talk since 4 years ago. We actually used to work at Target together, and we always wanted to do a purple team operation talk. And so now, finally on the stage, we get to do it.
Lucky us.
Lucky you. So my name is Kat Self. I used to work at Target, but also used to be a former artist and military intelligence, and now I am the macOS and Linux lead at ATT&CK. So for those of you that use MITRE ATT&CK, I'm the person that you get to talk to for macOS and Linux.
My name is Megan Carney. I work at Target right now, previously at Yelp. I do blue team stuff. I like to play outside. I like to play board games. That is my new handle where you can find me. That's about all.
So, of course, because we're going to attack, we're at least going to level set on ATT&CK really quick. It's open source. It's free. We try to be globally accessible. And most of you in here are actually contributors. So I've either cited your blog or your books or pretty much any of your publications or your videos. And you all have definitely been a huge, massive help in being able to make the macOS matrix much, much more robust. But the key point of this is the MITRE ATT&CK is actually all based off of observed behaviors of adversaries. Then we take that, we put a name on it, and then we all use the same name, so that way we all know what we're talking about. So when someone brings up spear phishing, we're all talking about the same term, and there's all of the associated detections, data sources, adversarial behaviors with that same word. So what we're going to talk about is we're going to talk about a little bit about community. We're going to talk a little bit about GitHub Resources that we're going to provide you all, and then we're also going to talk about detections, which I'm very excited about. So, and of course, we're going to talk about attack, which is what actually brings everything together, right? Like that's the glue that really brings these resources and actually makes them useful. Because we can talk about all these really cool adversarial techniques and drop some malware, but at the end of the day, if you can't use this in your enterprise to make it better, then it's not necessarily going to go over well when you run it in your environment. So, community. I got this beautiful opportunity to work with some researchers. Actually, when I first met Patrick at DEF CON, and I was working with threat hunters, actually, and we created a threat hunting workshop that we did at DEF CON's Blue Team Village. And 3 years later, we finally released all of the hunting playbooks. So this actually, if you go to the not-so-sketchy, very pretty QR code at the top right corner, you'll be able to find, it's the Hunt Apples website, but basically they're just attack-based techniques, hunting playbooks. And it kind of goes over like an actor-centric methodology, but it's a lot of resources that were done in researchers' spare time. So all the researchers are named at the bottom. They did some great work, but it definitely is a community-driven event. But it is mapped to attack, so there is that available for you. Also, the data set that they're using, there's no emulation code for it. There's just a data set that you can hunt on that we did the emulation on. So brings us to my very first talk at OBTS, for those of you that remember. We did a tree pose, and several people won a flag. But this talk was very specifically about attack, right? Like we're talking about OceanLotus today. This talk specifically covers like how to do CTI, specifically on OceanLotus, how to do threat hunting, how to do adversary emulation, and how to do assessment and engineering based off of what you found. We're not going to cover this. I just wanted to refer to this talk, because what we're really going to focus on is the actual problem at hand. But first, who is OceanLotus? So I actually drew this. I was trying to come up with ideas on like different ways and approaches to be able to describe OceanLotus. They had a big mass surveillance campaign where they compromised over 180 websites, and which kind of led to this, where it's like you're just kind of going about your day, but if you're in a targeted, like they're very targeted, so they will absolutely choose the environment in which you are working in. And so I kind of came up with this little cute OceanLotus baby, as my friend Molly calls it. And then we actually wound up making emojis out of this. So we'll be dropping those at the end of this. But the point of what we kind of came to is we had this great hunting, and then we had this great like how to use attack on OceanLotus, but we didn't have any actual emulation software. And then we realized, well, we have no environment to even execute this emulated software in. So there was actually 2 problems to solve. There was a really high bar to do stuff on macOS. So that was the biggest problem that we hit. And then also, Megan can speak to the detection side.
Yeah, so it was really useful to have an emulation thing to run on my victim machine and get like the full process tree, the full context, because enterprise environments are very noisy. And basically everything that an attacker does, a legitimate application might do. So in order to filter out false positives and make sure my alerts are viable, I need to emulate so I can test and then really focus down the detection onto what matters.
Yeah, so when she says that the regular applications do what malware does, that also includes dumping the keychain, thank you, IntelliJ products, and other things. So GitHub Resources that we're going to cover. You can thank this guy, Michael Butt. He actually is the one that created automated scripts. So for those of you that are struggling to be able to have a development environment, you can now automate that using Ansible playbooks and also Terraform. It basically spins up the environment that we use for the simulation. So it should be pretty quick and simple. So all that code is in our repo, and you can thank him for it. Actually, to kind of give you guys a scope of the emulation that we did, we had a month. We had a month to build out essentially 2 implants, the C2 server that goes with it, and then the entire plan, and test that and make it work along with the environment, and then get that set up. So it was an extremely tight timeline. So that said, when you're going through the GitHub repo, have just a little grace. But Melanie is actually the one that took over our macOS implant building, and then wrote Jakiro, which is the Linux version. Jared Stroud actually took over that development. So we actually have 2 different components, but we're only going to be talking about macOS 1 today. So we start with reporting, right? One thing that we noticed, you have to be able to have your C2 server be able to talk to your implant. So when we looked at the reporting, we specifically, thank you for all the screenshots from those that actually write these reports, we pulled this reporting. So 2017, was from Palo Alto, where they did these snapshots, and they kind of broke these down. Now, what this is, slightly cut off, is type length value. So when you're serializing binary data over the internet, there's a lot of different ways that you can chunk this out so that we can read it on the other end. And in this case, this is what we kind of observed. A lot of times when you're re-emulating software, you're taking in multiple reports and points of contact, and you're trying to understand, like, what is it doing? What's the common patterns here? Because that's going to be what I need to emulate to be the most effective. And so that's kind of what we took it from. We took it from the Jakiro. We took it from the Unit 42. We then identified the descriptions and then wrote those down. And then this is essentially what we emulated. The top one is going to be the macOS specific, and then the bottom one is essentially what we pulled from both of them. I point this out because if you guys are going to go in and play in the code, this is going to be what it expects. And the reason why this is important is because this little guy right here, these values were actually the same in all of them, but those are byte indices. So it actually has an 82-byte header, and then after that header is essentially all the data, whether it's going to be the data that you're going to send back from the implant or whatever. And so that 82-byte header is very, very specific with very specific constant values at different indices. And so it's going to automatically look for those indices and those specific byte values at that point. Note about the macOS one. Back in 2018, they actually transitioned to HTTP, which is actually where they went and took the same serialized data, popped it into the payload section, and then popped it onto an HTTP packet. So we were like, OK, so that's what we're going to do. So that's how we emulated that. So it's slightly different than the Jakiro one, but it still uses that process. Now, as I said before, if I'm an adversary and I want to talk to my implant, how do I go about doing that? And then this is essentially how. What we did is we took this command. This is the structure of our commands that we use a Python script for. We send it to this Python script. This Python goes to our Magic API, which is our C2 server, essentially, that we can use to transform into these different implants. Then what it does is it talks to our actual handler. Inside of our handler, we have 2 specific components. This is going to be really 2 data structures that actually take that data, transform it into what the implant is going to expect, and then parsing out that data. And then the other one is going to be the checksum, do the indices with this constant values match what I'm expecting? So we take that command, we actually translate it into what it expects, which is 0xAC, because in 2018, they actually switched their commands from 4 bytes to 2, and then they went to, anyways. So transform the command, it checks the sum, and then it goes to your Apple host. The nice thing about this is that if you don't have that checksum in place, then as a result, like, you can't connect, it'll just drop the packet. So this all actually comes from a 2017 report. What's kind of interesting about this is the fact that we realized, it actually took us embarrassingly too long to realize that they were always talking about the same implant all the way up to 2020. We thought they were talking about different implants because the titles of these reports say, new macOS backdoor discovered. Turns out that's a lie. It's the new dropper of the same macOS backdoor discovered. Took way too long, but this is in 2017, so nothing really largely changed out of the implant. But there is a reason why this is misleading. And so when you kind of start reading reports, you have to pull out these commonalities, right? In this case, it's using DL open, and then it's calling the DL sim. So what's significant about this is that this was also discovered in a Linux version in Roto in 2021, which was much later, which is actually active since like 2022. But this required us an attack to be like, okay, we're emulating this. You get a really different perspective when you're actually emulating software. When you're actually looking at code and trying to recreate it, you have a different problem set to solve. And so we realized, we probably should update this technique, because right now it's only Windows. So as of October, this is no longer Windows. This is going to be Linux and macOS, because this actually includes the shared objects for the Roto, and it includes the dilib files, which are essentially the shared objects for macOS. Now, taking that reporting, there's a couple of ways that you can use this, right? An application, right? Because at the end of the day, as we started off, if this isn't useful to your enterprise, then you're probably not going to really be allowed to run malware in your environment. So, self-created malware in your environment. Atomic testing is one way to be able to apply attack in this regard. What you do is you take an attack technique. In our case, we're going to take shared modules. Then we're going to choose a test. Again, this report, right? We always base everything off of open source reporting. Using this report, we're going to create our procedure, and then we're going to execute our procedure. I have found through different Purple Team operations that it's really, really important to cite your code of when this technique actually happens. The reason why is you will be on a phone call, and they're like, no, 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 I totally detected it. And you're like, no, what you're talking about is not the actual thing that I did. And they're like, yes, it is. And then you're like, you have to show them the actual code that you ran. And then they're like, oh, yeah. No, that's not what I detected. So it's really helpful when you have that transparency. But as someone that's using other people's code, it's really helpful when you know where to go in the code when that technique is actually being called. So, and then last, I'll let Megan talk about the detection.
Yeah, so what you're looking at right here is a screenshot of Splunk. I took the victim data and I brought it into Splunk for analysis, and you're looking at the endpoint security framework event for memory mapping. And what it's showing you here is that this file was loaded. So memory map in this case is a fancy way to say it loaded this dilib.
And then that's shared modules for the atomic testing. So here's what we actually emulated regarding shared modules. Here's the actual code. We always try to cite the actual CTI inside of it, so that we can always go back to that. And then we always try to highlight where the actual calls are made, where it actually calls, and then loads our dilib. Now, the reason why this is significant is because of this guy right here, where there's actually two specific commands that run a dilib differently. Because we don't necessarily have reverse engineers on our staff, we don't get to just pull down that implant, reverse it, and then recreate it. So we have to base a lot of these things off of reporting. What this is called is implicit reporting. And that basically means there's not a procedure code that we can just copy and paste and run. That means we are given a capability, and then from that capability, we can extract an understanding that this is a behavior that we should probably emulate, which is what we did. And so in this case, the way that OceanLotus specifically uses it is they actually have broken out their network communications traffic into a dilib. So they've successfully modularized, and this is just a note, this is back in 2017. So this is not recent at all. So they have their main implant, which has all their commands to be able to translate what to do on the actual host, but then it uses those same system calls to be able to actually load that dynamic library in to be able to connect to the C2. And then with these additional commands, they can then download a dilib and then execute functions from that dilib on the actual host. So This is essentially the full scale of what we actually emulated before I transition it over to Megan to talk about all the different ways that you can detect what we did. We have macOS Catalina. This is what was based on reporting, and at the end of the day, we always have to go back to CTI. So we based this on macOS Catalina. We then created an app that looks like a Word document, and then once that app was downloaded and double-clicked on, then it launched a bash script. This was kind of a jumble between 2017 and 2020 reporting. After this bash script goes, then it opens up its Word document, right? Because you don't want the user to think anything suspicious is happening. So you're going to open your Word document that you expect to see. And then install the launch agent in the users directory, and then it takes base64 encoded, drops 2 files. These are going to be those 2 files that we talked about, where it's that network communications library and also the core implant. And then it's going to the core implant, which is a Mako. It's going to execute the Mako, delete the app, and then finally it's going to actually reach out using its dilib file for network communications to the C2 server. And then, of course, since there's no reporting, thank you, by the way, for everyone that spoke on the Lazarus group, for all of the hands-on keyboard commands and the lateral movement callouts. I really specifically appreciate you all, because there's no reporting for OceanLotus on lateral movement, so we kind of had to take a lot of implicit reporting and being like, well, they use services, this could be what they do, which is what we did for the SSH. So they look for SSH keys, find that this is actually an admin for a Linux server, or they do file transfer, so it's very normal for them. They take their keys and then move over our Linux component, which continues this scenario, which is out of scope for this. So this is kind of our final product. The reason why we actually have this structured like this is because we have the actual activity of the red teamer, and then we have a kind of a visual aid, and then we also have the attack techniques. And this is really helpful when you're trying to communicate to other teams and parties what's happening, because everyone's a different type of learner. And it also gives you the additional resources, because it's all based on attack, to be able to go a little bit deeper. So even if you don't know what this is, if you're an analyst looking at it and you want to understand the behaviors deeper, you can then take these attack techniques to the bottom and be able to do your own research, and not necessarily have to ask a lot of embarrassing questions during a meeting. And now I got to turn over to Megan.
Yeah, let's talk detection. I need the power. Thank you.
Magic wand.
Exactly. All right, so before we get into details, I want to talk a little bit about Defender's Advantage. If you have a SIM that is centrally collecting logs in your environment, you can define what's normal and what's not normal. This is incredibly powerful. I think a couple people have talked about it already, and we're going to return to this theme later. So, OceanLotus installs an unsigned launch agent. And one of the pieces of advice I hear a lot is just alert when you see unsigned launch agents. So what happened in our environment of 7,000 plus machines when I implemented this alert? It was a disaster. We were getting 2 to 3 false positives on the very worst days, and that was with me constantly updating an exclusion list. And before I talk about all the ways in which this alert fails, let's talk about the ways in which it works. This alert specifically targets attacker activity. That's a good thing. Basically, it makes the attacker unhappy, and I like that. I can test this. Now, this sounds really simple, but if your logic is super complicated or dependent on some sort of machine learning magic black box, this might not be true. But everything else is terrible. So my security operations center was very unhappy with me because I was wasting their time. And I'm not happy either, right? Because if this alert ever fires a true positive, it's going to get ignored because it was so noisy already. So instead, I tried implementing firing an alert every time we saw a new unsigned launch agent, where either VirusTotal didn't know about that binary or knew that binary was bad. And this has only had 1 false positive since I put it into place, which is pretty awesome. So let's zoom out a bit and talk about how you get to better. You start with your indicator of compromise, in this case, our launch agent. And then we talk about context and enrichment. And some of this is external, things like VirusTotal, and some of it's internal. Remember I was talking about Defender's Advantage and defining what's normal for your network? That's the kind of context you need to get to better alerting. So everyone's happy, and we're all good, right? Actually, we're covering several different pieces of malware here, so that's good. But there's a problem specifically with OceanLotus. OceanLotus, at least in 2020, backdated the plist. So I can't assume I'm going to find the plist based on it being a new file. Unfortunately, I also can't just alert every time I see touch backdating or timestamping a file, because a bunch of dev tools do this. This is the problem I became obsessed with solving, because it's not just about touch. It's about all the other commands that CrowdStrike talked about. Xadder, security, shushmod. These are all used by various tools in our environment. It's super noisy. So what does it mean to talk about context for things like living off the orchard or living off the land binaries, whatever you want to call them? I started by asking, has this exact command been run in my environment recently? Has this responsible process run this command in my environment? And how common is that responsible process? Am I used to seeing it? And then, yeah, we're going to look at VirusTotal too, though don't rely on VirusTotal completely. Some things that are not benign are labeled as benign, and some things, yeah, you all know this. Okay. Anyway, I've decided to call it Normalized Baseline Detection. I had to give it a name. But also, I thought the acronym made sense. The idea of establishing a baseline, comparing it to a sample period, this is detection 101. So what does an example of this look like? Here we have, there we go, our Xadder command. This is the quarantine attribute being removed from Google Chrome by Google Software Update. And this is what we see in our baseline. And in our sample period, we see the same exact command with the same exact responsible process. So we can say that this activity is not suspicious. It is what we expect to see in our environment. From a high level, this is what the code looks like. We have our baseline period, so we're going to look at all the instances of Xadder in the baseline, all the instances of Xadder in the sample period, and then for each of the instances in the sample period, I ask, is this new? And is this responsible process command pair new? And if the answer is yes to either question, we're going to enrich that record and write it to the SIM. In this case, I define my baseline as 14 days. My sample period is 1 hour. Go back as far as you think your SIM will allow you to before it crashes. All right. This code looks simple, but we really quickly get to some questions about what is new exactly, because life is complicated. The first reason we get to complications is because there's a bunch of noise in the data. Things like Xadder, I only care about when it's doing certain things. Things like System Profiler, I care about all the time. So for some commands, I only want to pick them out for analysis when they're using specific arguments. And sometimes I need to ignore arguments entirely. So I apologize for the eye chart here, but what we have here is an ifconfig command with an interface name and an IP address, and we have a very similar command down here. If I do a character-by-character comparison on these commands, they are not the same. So very simple, very simplistic analysis would say these do not match. But they are functionally the same, right? Across different machines, your interface names and your IP addresses are going to change. So for some commands, I just need to ignore arguments entirely. And then we get to normalization. So here again, we have something that looks different, but is functionally the same. These are temporary directories. Let me see if I can get the spotlight to work. Created by the installer binary. So this is actually the same process doing the same thing, and this activity is not suspicious, or shouldn't be labeled as such. All right, after we get to all of that, we get to some very weird process trees. For some reason, this happens a lot with System Profiler, where the responsible process is itself. So I need to go hunting around in the process tree and find something more interesting and useful. And then after all of that, I still need more context. New is interesting. It is not necessarily bad. So we're looking at how common is this responsible process hash, And how common is this responsible process path? Because what I found with developers is when they're compiling tools on their own machines, the hashes might be unique in your environment, but that doesn't mean the binary is actually unique. So, yeah, and we're gonna look at virus total too. So, to get back to where we started, how does this help us detect OceanLotus? These are the 3 touch commands that we observed in the emulation. This is the plist. It's making me dizzy. All right. And our responsible process in this case is the bash script inside the decoy application. So what are we going to write to the sim when we investigate this process? We're going to start with the reason for the alert. It wasn't seen in the baseline period. This is a new instance of touch running. And then we're going to look at the process. So you'll notice I have normalized the command line here because we need to normalize responsible process names and command lines. And then I have the real command right here. And then we're going to look at the responsible process, which in this case is kind of useless because the responsible process is bash, and bash exists on basically every host in the environment. And the virus total information is also kind of useless because bash is benign. However, in this case, this is all I need for my rule. Just by looking for unique instances of touch running, I was able to filter out the noise and get to viable touch backdating, except for this stupid app, because life is still complicated. All right, so this is a relatively simple example. I've also been able to do shushmod and xadder with this method. And there are a bunch of details that I could not fit in this presentation. So they're up on my GitHub. I will also post them up on Mastodon. I'm playing with some other baseline detection ideas for process trees, for things like Microsoft applications, think malicious Word files, or malicious PDFs. That would be fun to play with too. Yeah, that's my bit.
So yeah, we really just wanted to cover, as far as key takeaways, when you're building out emulation plans, focusing on that pyramid of pain. David Bianco's pyramid of pain is pretty notorious. I didn't put it up here because we don't really need it. All of you probably know it. But that is really where you want to focus on. And
yeah, and in your red team reports, which I love to read, please give me process trees, like full process trees with the responsible process, because I can promise you that in like 95% of the cases, that process activity exists in my environment, being used by legitimate applications, and if you don't give me something to filter on, and I have to maintain this exclusion list that has to be updated every week, that rule is not going to stay in production.
all right, so questions. All of the links actually provide all of the code and the resources that we have. The bottom is the detection. The top is going to be Adversary Emulation Library, which is currently published. We'll be releasing a technical blog later on this week or two. And then last but not least, this is actually going to be the first adversary emulation plan in the Adversary Emulation Library that if you want to actually contribute to, there's functionality that we weren't actually able to implement, such as the obfuscation and the encryption, those 2 run commands that for the dilib, for the shared modules, we weren't able to implement. So if any of you want to do it and contribute code, I'll be the reviewer. And so you can always hit me up. So thank you guys so much for everything.